everyone, welcome back. This is the class of ECE 350, the principle of automatic control. This is the second class. This is the lecture for the first week Wednesday's class. All right. Actually, last time we go over the syllabus, and now let's go inside the course. Yeah. ECE 350. This is for the first week Wednesday's lecture, and now we start from an example of a system, a control system. All right. Example of a system. Example of a system. We consider a circuit. This is a kind of source, and here's I put the R as a resistor, and then the capacity C. Okay, just like this. And this side we have a voltage as a resource E of t. So the voltage here is E of t. Its value will change according to the time. At different time, the voltage might be different. Then we measure here as the output V of t. So this is the input. This is the output. Now this is system. You can also think this is a kind of a command, and this is the response. The same meaning. You can call this as a response or output. This is the input or a command. Alright. Then we want actually basic problem is for given E of t, what will be V of t? So to find this V of t, first of all we need to find something like a relation between E and V. Then when E is given, according to that relation you can find what is V. Right. So for this circuit, okay, we need to write some equation, right, to find the relation between E and V. Suppose here's I. Then I times R, right? This will be the voltage here. I times R will be voltage here, and the voltage here is V, right? That will be E, right? Yeah. And we need more equation, right? Because we have E is input, V is output. Now we have I, so we have three variables, right? Three variables. I is also a function of t. So we have three, but just one equation. We need another equation so that we can erase this I. We only need a relation between E and V, input and output. For I, yeah, this is capacity. So as a capacity, we have I will equal to what? This is C. C times the derivative of the voltage. Right. So we have these two. Okay. Now we have two equations to describe this system. We can try to erase these. Which one we want to erase? We want to keep E and V, right? We want to erase I. Okay, just plug in that will be fine. We plug in, then we have C times derivative, then times R, right? So CR times the derivative of dt plus V equal to E. Alright. For simplify, you can write it as CRV prime plus V equal to E. Right. Here, just write the derivative by prime. You can also write this as V dot. You put the dot over it. It's also fine. The same meaning. These three notation, the same thing. Okay. So we have equation. Then from this equation you can see E and V, only E and V, right? CR are given. CR is some value given in the circuit. And if E is given, then the only thing is you need to find this V. This is what kind of equation? This is a differential equation, right? So we need to solve this differential equation. If E is given, we solve it, we can find what is V. So this is a kind of a physical way to study a system. And here we have some names, some concepts. This one, we call this as a state equation. State equation. This is state equation. So we have input, output, input. We have output, I/O, right? Input, output. This is also output. Right? This is also output. This is also output. But we have I. I is what? I we call it as a state. We have some other variables. Yeah, some other variables. The variables other than the input and output, we call them their state variables. State variables. So we call this kind of equation as state equation. Usually you start from the system, electrical, like this is circuit, or some mechanical, or even some other kind of system. You can write some equations. Then you call this as state equations because other than input output, you have some other variables. We call them as state variables. So these are the state equations. We need two equations to describe this system. For this example, maybe you have more complex system. You have dozens of equations to describe that equation, that system. Yeah, that kind of thing, a state equation. And this equation, now we have this one. This one is quite simple. We only have input and output, right? Input and output. And CR is a constant. This is a constant. This is a constant. Some constant. Right? So this kind of system, we call this is the dynamic. This kind of equation we call it dynamic equation, or you can call them as a I/O equation. These are only contain input and output. Right. So this is for a system. Yeah, this is just example, but we can have more complex things. We can have some more. System. We can have like a state equation. For example, we have x1 take derivative equal to 2x2 plus u of t, and x2 die equal to 3x1 plus 4x2. Okay. And y equal to x1 minus x2. This is I give three equations. So you come this equation is coming from some system, some mechanical system or some circuit. And here input is u, output is y, and the state I have x1 and x2, but more complex than this. This one already have I as a state. Now I have x1, x2, two state. Okay. You can have equation looks like this, or equation, the I/O equation is a dynamic equation. For example, I have y with 3 times derivative plus 4 of y prime plus whatever 16y equal to this side is u prime plus u, like this. Here's a input is u and output y. Okay, so this is a system that makes equation already contain input and output. Right? You can have more. You can give even more, right? You change the parameter to be different numbers. You have different system. And here the highest derivative is 3. Maybe you can consider more complex system. The derivative as high as like 10 times derivative, even more. Right? That depends. Okay. All right. These are the system. We study one example of system. Now the problem we need to solve it. Right? The basic thing is if E is given, what is V? E is given, what is V in this example? Right? Then how to solve it? We use MATLAB. Not MATLAB. Right? Yeah. Later we can learn something. How to use MATLAB to solve an equation. But now we should know the basic thing. Use the Laplace transform. Laplace transform. So give a name for that equation. I call this equation as equation 1. Equation 1. Okay. Now we try to solve this equation. To solve equation 1, we need by Laplace transform. Laplace transform. So, of course, first of all, we know what is a Laplace transform. What is a Laplace transform? So, we go here, the definition of Laplace transform. We start from a signal, a function according to t, right? Function of t. Then Laplace transform will be I put a capital arrow here, means Laplace transform, and here's an arrow. Right? We will have a function capital F, a variable s. Now here is a lowercase f, is capital F, the same letter, but one is lowercase, one is capital letter. And the lowercase letter we use it for signal for function of time t. And this capital F means this after the transform. That will be a function capital F with variable s. S is in different variable. Let's see what is the f of s. It is an integral from 0 to t, and the given signal f of t times e to the negative st dt. Alright, so it is this one. You can see here ft has variable t, and e to negative st you have variable s and the t. Then we take integral. We use t to perform the integral. So after we do the integral, this result only depending on the value of s. So we get a function of s. For different s, you have different value. Right? When s is changing, then you can have a value of s, a value of f. It's capital F. So this is a function of s. So this is the definition. This is definition. For integral, that is just a normal thing. But s here, s is different. S is a complex variable. Or we say a variable has a complex number as its value. It's a complex value, like a plus b j, things like this, like 1 plus 2j, negative 1 plus 6j, things like that. We have a real part and an imaginary part. J is the square root of negative 1. So s S could be valued any kind of number looks like this. Not just the real number. T is real number. T is time. It must be real value. This must be real value. But S is complex variable. Its value should be a complex number. Right, so this is the definition of Laplace transform. Okay, then we try to use this one to solve the equation. Equation 1. Equation 1 is here, right? Equation 1 is here. We try to solve it. So we perform Laplace transform on the whole equation on the both sides, right? The left side, right side will perform Laplace transform on them, and we will see the result will be give us the some result is better to solve it. Yeah, you can see. So here, of course, CRV prime plus V equal to E. This is equation 1, and E is given. It's given, but it could be anything. Here we just suppose E of t is like 1 and 0. T larger than 0, it is 1, and t smaller 0, it is 0. So E of t looks like this. This is t, this is E, its value is 0, 0, 0. Okay, here jump to 1 and keep to be 1. Now you can think this is kind of a switch. You turn switch on, and you have this E of t. We call this as a unit step function signal. And we denote it as US of t, unit step function. So this one we can also write it as E of t equal to US of t. We can also this part we can also write in this way. Yeah. Et equal to US of t. Then what is V? Yeah, makes sense, right? You have circuit. You want to give a voltage. You have a battery. You connect it. At the time 0, you connect it. Then you have a voltage. Suppose the battery has voltage 1. Then, okay, what will be the V? Right. Now we perform Laplace transform. The E of t. This is a US of t. We'll perform Laplace transform. We will have US of S. Alright. Yeah, here US is just this US. And this S is the variable. Okay, these two S are different. This S is coming from here. It's a part of the name of the signal. And this S is variable. This is T, this is S. And sometimes we call this as the signal in S domain. S is the domain of this function. We call this a signal in S domain. And what it is, okay, by definition, this is 0 to t, and US of t, the given signal, times e to the negative st dt. Alright, now just some math, some calculation. 0 to t. And of course, here t means positive side. Right? So t is positive, t is larger than 0. And US of t, for positive t, it is 1. So this is just 1 times e to negative st dt. Okay, remember what is the integral of this one? Yeah, this is a 1 over negative s e to negative st. Right? Remember, this is exponential power. You take integral, it will be this one. Right? Reverse of the derivative. If you take derivative, that will be negative s times. Now you go back. It's an integral. Go back, and the t will run from 0 to t. Yeah, a little bit confused, but this t is the upper bound of the input, and this t is the variable. Right? Okay. Now, if you want to make it more accurate, you can write this as a tau. As a tau. Here's a t. Here's a tau. Right? Here will be tau. Here will be tau. All right. Then plug in. It is a negative 1 over s times e to the negative s twice t minus this is 0. Okay. I think I get something wrong. Laplace transform. Oh, there's no t. This is infinite. It's my fault. Okay. Definition. Here. Sorry. Yeah, integral. Here's an infinite. Positive infinite. Not t. Not a t. Then there is a t. Okay. And here will be infinite. Here will be infinite. Now here's a, yes, still t. This is infinite. The t runs from 0 to infinite. It's a t. Okay. It's a t. T. Alright. Then t now is infinite. And the minus this t0, the e to the negative s times 0, it's a 0. Okay, then we have negative 1 over s. When this go to infinite, you get 0, right? You get 0. 0 minus this e to the 0, it is 1. So we have negative 1 over s times negative 1 is 1 over s. So E of t by Laplace transform, you get 1 over s. Okay, this is one side. The other side, v prime and v. Equations. V prime plus v. We need to perform Laplace transform. V is something unknown. So v by Laplace transform, it is just a capital V of t. We don't know what it is. We don't know what it is. This one now. And v prime of t. Okay, this one by Laplace transform, u over v1. Yeah, this one actually we have a formula for this. We can apply that formula. I didn't give you a formula right now, but I can write it. Just write it. It is s vs. S times Vs. Exactly speaking, we still need some initial value, minus V of 0, like this. This one by Laplace transform will have this. And here, for simplify, we just suppose, the system looks like this. Before you give battery here, you can think of there is no voltage. Right? Voltage is 0. So the voltage at the time 0, it is just 0. This is 0. This is 0. This is just 0. So this is just S times V of S. Okay, so 1 becomes CR times V prime. After Laplace transform, we have S times CR S times Vs and plus Vs. Equal to E. E now, after Laplace transform, we have 1 over S. Okay. Then we have CRS Vs plus Vs is 1 over S. So here, CR given. V is unknown. Now we can solve it, right? So V of S times CRS plus 1 equal to 1S. So Vs equal to 1 over S divided by this one. 1 over CRS plus 1. We have V of S. Then the problem is we do an inverse Laplace transform. We can find the V of t. Okay, so this is the basic idea to find this v of t. Of course, we didn't finish. We just get this one. We get capital V of s. This is the function in s domain. Now we want to know what is the time domain. What is time domain? Okay, this is the problem. Definition of the Laplace transform is here. We have this definition. When f, lowercase f is given, you just follow this formula, you can find capital F. But if capital F is given, what is the lowercase f? That is a hard problem. That is a hard problem. If you calculate directly, that will be hard. So what we can do is, we start from f of t. We find capital F. Then you know that capital F, if you go back, must be that lowercase f. For example, now we know for inverse Laplace transform, we know 1 over s go back will be us of t. We just calculate, right? We start from us of t, we find the Laplace transform of us of t is 1 over s. So we can know the inverse 1 over s go back to time domain must be this one. Okay, so by this way, we can have a list of result. Some function on s. Then by inverse Laplace transform, we know what is the signal, the original signal. Yeah. So the same thing. We work like this. And here for this one, actually, yeah, we have this result, but to find that result, it works like this. We start from some signal on t, then find what is the Laplace transform. And among those signals, one of it will have a Laplace transform looks like this. Then we know, okay, that one is the inverse of Laplace transform. Sounds good, right? If you do not have enough information, if you do not have enough result here, then you have to try to do it. You select the signal and try to find the Laplace transform and to see whether this one is the same as your Laplace transform. That will cost a lot of time. But fortunately, we have tables. That means some people, they already find Laplace transform for different signals and they list the result there. And we can just use that result. That is a table of Laplace transform. Table of Laplace transform. I have the table here. This is blackboard. And I just added. I have announcement, syllabus, then lecture materials, and the lab materials. In the lecture materials, click on it. Oh, the internet is slow. Sorry. Okay, see, I put the tables, the Laplace transform, and the Laplace transform 2. I have 2 tables. Let me open both. Okay, the first one. The first table is zeron of Laplace transform. Make it large. Yeah, zeron, or you can say cordon properties of Laplace transform. Yeah, like this one we just discussed, right? The derivative of the signal, we just use v of t take derivative. Then perform Laplace transform where equal to s times v of s. Right? Now is in generally for f of t take derivative, then find what is the Laplace transform. It will be s times this capital F s minus f of 0 is the initial value. this value, usually it means the value for 0 in the negative side. Make sense? Like in our example here, we suppose the input is you turn switch on, or you add the battery on this as a source, right? You turn the switch on, then you have a voltage like a 1.5. You have battery, small battery, A battery. Put it in, you have voltage 1.5, or you can just suppose you have a power that is keeping 1 voltage, right? Is 1. Before 0 you have 0. After 0 you have 1. But at the point 0, what it is? It is 0 or it is 1? Okay, you can think 0 is not just 1 point. 0 is a small interval. You can think like that. At the beginning of 0, you get 0. At the end of 0, it turns to be 1. And this F0 is the beginning of 0. At the end of the 0, the value were given by that function, f of t, by that function. And before that, you can have different values. So this f, you can say is this 0 is looks like things like this. Let me write it somewhere. Let me write on my notes. So f prime of t perform Laplace transform or equal to s times f of s minus f of 0. Okay, I put the minus here. This is the negative side of 0. Right. This is 0. This side is 0 minus, and this side is 0 plus. 0 plus. Usually, when you turn some, like you turn the system on, then before you turn it on is in the 0 negative side. This is t. T is 0, but the negative side before you turn it on. And this side is t. Time is still 0, but in the positive side. This is on. Like the switch looks like this, right? So this side is 0 minus. This side is 0 plus. The u of 0 minus, you think it's 0. And u of 0 plus, you think it is 1. Things like that. This is the switch. This, yeah, things like that. Okay, so this is one of the property in the table. Right, we just use this, and here we have more, not just this. You see, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9, right? 1, 2, 3, 4, 5, 6. Oh, 10. There are 10 properties, or 10 formulas, or 10 zeros, right? Yeah. And I suggest after the class, you look at this table and go read it from beginning to end. One line, try to understand what are they talking about. Understand all these terms. Understand the meaning. It is not necessary to remember, but try to understand the meaning. Okay. And yeah, maybe next time I can discuss more about it. Yeah. This is the first table, and second table. Okay, this table gives us a list of signals and its Laplace transform. You can see here. This is a time function f of t. Here is a Laplace transform f of s. Right? We have these two columns, and this side is also 2 columns. Okay, then 1 over s related with unit step function us of t. Right? We just define these, and actually we have more. We have like a 1. This is a unit impulse function according to 1. The unit run function according to 1 over square. Yeah, I will explain this later. Now we want to find s times. We want to find want to find 1. Here. It's 1 over s times something times s plus 1. Some number times s plus 1. We want to find this one. Can we find this from the table? If we can, that would be great. Can we? Okay, just go over along the column of transfer of f of s, capital F of s. You see, we get this one. You got it? Yeah, this one. Okay, now we have it. Let me write it. Now, by table. Table of Laplace transform. It is, let me copy it in my notes. Okay, 1 over s times s plus alpha in denominator, according to 1 over alpha times 1 minus e negative alpha t. Okay, I copy this line, this pair, right? I copy this. Now let's go. Okay, yeah. By the table of Laplace transform, we have this one. We have this one. Then we compare these with these. Okay, not exactly the same, right? This is some constant times s plus 1. Here's I need s plus r. So I need to make these, we change these a little bit so that this one can be exactly apply this one. All right. So now v of s is 1 over s times CRS plus 1 equal to, we want to write it in this way. 1 over s is okay. This is a s. Right? This we need a s, so I move this CR in front of it. So CR, 1 over CR in the front. And this is s times, okay, CR moved, so CR is moved, so I already have s. And here's 1. After you remove CR out, you need a 1 over CR here, right? Like this. Okay, now you compare these two. We know alpha is what? Just 1 over CR. This is alpha. This is alpha. Alpha is just this 1 over CR. So, inverse Laplace transform, it will be, okay, this is constant. I just keep it. Keep it. And this one, I use this term in the table. It is 1 over alpha. Now alpha is 1 over CR. This is alpha. This is alpha. This is alpha. And times 1 minus e negative alpha 1 over CR times t. Alright, we got it. This is a V of t. This is V of t. V of t. So we know V of t or equal to, we can do some simplify, right? This one, they can be cancelled. It is 1 minus e to the negative 1 over CR times t. Okay, you got it, right? I can give a graph to show the relation. Input is a unit step, and this is result. I put the result here. Input is a US of t, unit step. It looks like 0, then 1. Here's a 1. This is US of t. Here's a t. This is the input. And output, we have V of t, which is, well, negative side it must be 0, right? It is 1 minus e to the negative CRT for t positive. For t positive. If you want, you can also write 0 for t negative. Negative. For negative side, it is just 0. You just write this or will be fine. Just this will be fine. you can also write it as 1 minus e to the negative CRT for all the t, but for negative t is 0, right? So you multiply by us of t. You got it? Because us of t, this is us of t. Positive side is 1, negative side is 0. So when you multiply us of t on any signal, that means you keep the positive side times 1, right? Keep the positive side, totally same. And make the negative side to be 0, because 0 times it. No matter what is the value here, after times 0, you get 0. Okay? Because here is 0. Yeah. And we can also have a graph, how it looks like. Negative side, it must be 0. And the positive side, it is just 1 minus this one. When t is 0, okay, t start from 0, 0 then grows larger and larger. The t start from 0 and go up, go right side, right, to positive side, larger and larger. When t is 0, this is 1 minus e to the 0. So e to the 0 is 0. So 1 minus e to the 0 is 1. So 1 minus 1, you get 0. So this point, it is 0. And when t increase, this one, you see, it is a e to some negative power. So when t increase, this one will decrease, tend to be smaller and smaller, right? So it will be, is 1 minus some number, but you mind that this is 1, right? It's 1 minus, at the beginning is 1 minus 1. And then 1 minus something less, minus something less. So the result will look like this. Looks like this. Alright, this is V of t. V of t. At the beginning is minus 1. This is 1. Then when t increase, this part will decrease. When t go to infinity, this part will go to 0. So 1 minus 0 is 1. When t large enough, it is almost 1. Right? So the output looks like this. Alright, now makes sense, right? We can go back to the circuit. What is the circuit? Here the circuit, right? Here the circuit. Here the circuit. And the response. When E of t, here you give a voltage, you apply a voltage 1, here, start from 0, then turn to be 1. Then what will be output side? It will be 0, then turn to be 1. Still turn to be 1, but it increases in a smooth way, not just jump up. Right? Here you turn this, like you have a power, you have switch on, you turn it on, then the power is on, then okay, you get 1 voltage at once. Just at this time you get 1. And output side, it is also grow up to 1, but smoothly, not just one jump. It increase gradually, finally reach 1. So if you keep this, here's a fixed power, keep for a while. Then this side will also same voltage with this one. The both sides you will have same voltage. But at the beginning, the first few seconds, depending the C and R, depending on the value of C and R, the graph here might be different. Then in the beginning, it will increase for a while, start from 0, increase to 1. Yeah. So this is the whole response of the system when you put this step function, unit step function. All right. Okay, so this is one example. We can also study for this system with different input. Now we just unit step, right? If we use, for example, we use a different signal, like we use an impulse, then the Vt will be different. If here's like we put a sinusoid, like a sine omega t, here will be something else, also different. And all of these we can use the same way. You perform Laplace transform you perform Laplace transform on this equation. Sorry, several pages. I confused which one. We perform Laplace transform on the equation, and one side we have unknown, and the other side we do not have unknown. I put it somewhere. Not this one. Not this one. Oh, it's here. Right. Yeah, it's here. Okay. Yeah. Right. Equation 1 after Laplace transform will become this one. Here, this is coming from u s of t. Unit step. Go to here. Laplace transform. Right. If this one is changed to be something else, different, then here will be different. This side are same. This side is same. Then you can do similar thing. You move v of s in the front, and then divide it. Right. You can move v to the front times v CRS plus 1, and this side will be something different if you have different input. This will be different. Then you can have something looks like this, but this is not 1 over s. This will be something else. Okay, then you can try to do similar thing. You go to the table, try to find this one. If you can find it, then you can have the solution just based on the table. But sometimes maybe you cannot. Then you need to make some change so that you can find it from the table. That means you try to rewrite this as it's a combine of some simple part, and each part are listed in the table. Each part is listed in the table. Then you can solve it. It's like a basic idea about how to solve a system. Alright. Okay. I think that's all I want to give you today. So it's the time 47. I have 3 more minutes, but it's fine. We can see you. We have 3 minutes, but I'm done. So see you next time. Bye bye.